Today's lecture deals with the topic of polarization of electromagnetic radiation. Now, before we can talk about this property that we call polarization, we need to review some of the properties of electromagnetic waves if we're ever going to understand the cause of polarization. So remember back to our discussion on wave theory. We classified all waves as being either mechanical waves or electromagnetic waves. And for mechanical waves, our classification scheme involved wave subclasses, that is, transverse, longitudinal, and surface waves, describing the direction in which the particles in the medium were displaced. It turns out, that electromagnetic waves, by their very nature, are transverse waves, three-dimensional transverse waves. And although they don't require a medium for propagation, when electromagnetic waves do travel through matter, they displace the charged particles in the medium, like electrons, in a transverse direction, perpendicular to the direction in which the wave energy travels. More on that in a bit. So when we talk about what causes electromagnetic waves, it is accelerating charged particles. Very often electrons that causes a combination of changing electric and magnetic field vectors. And an electromagnetic wave is really nothing more than this oscillating pattern of electric and magnetic field vectors that propagate through space, in a vacuum at the speed of light. So what you're seeing here in the figure is a snapshot of a wave emitted by a single atom, at one instant in time. And you notice here that, the red, this shows you the electric field vectors at various positions in space. And you'll notice that the electric field vectors are wave-like, that they change in a sinusoidal fashion. When you look at the blue, let me get a laser pointer here. When you look at the blue vectors, these represent the magnetic field vectors of the electromagnetic wave. And these two, you'll notice this changing pattern in the magnetic field vectors, follows a sinusoidal wave pattern. And then, of course, we have the direction of propagation. Notice that at all points, the electric field is perpendicular to the magnetic field, which is perpendicular, to the direction in which the wave and thus energy travel. So when we talk about polarization, the direction of polarization is the direction in which the electric field oscillates. It's really the direction of the electric field. And although the electric field may change in time, when you look at this picture here, you see that the direction of the electric field, is in one dimension here. And that one dimension will be the direction of polarization. So what you saw illustrated on the previous slide was a single electromagnetic wave emitted by a single atom. So when we talk about unpolarized light, a real light source consists of kabillions of atoms with kabillions of vibrating electrons that give rise to kabillions of waves simultaneously. Now, we can't possibly draw kabillions of waves, but to show that light is unpolarized, we will take a look at a model here, a way to represent that. So for a beam of unpolarized light that is traveling or propagating in the plus x direction here, the electric field vectors of the individual waves could be oscillating randomly in the YZ plane. Now I'm showing you about, let's see, 1, 2, I'm showing you, 3, 4 electric field vectors here in the YZ plane. So this would represent, 4 atoms of light. But notice that the electric field, if each of these vectors represents the direction in which the electric field can oscillate, notice that they are randomly situated in the YZ plane. Here's a picture that kind of shows you 4 different waves, okay, the blue, yellow, green, and red wave, okay, where the direction of the electric field, if these show you, if this is the electric field wave here, they show you that it is randomly oriented, okay, perpendicular, in the plane perpendicular to the direction in which the wave travels. Now, another representation, at any given point in space-time, the resultant electric field vector is the linear superposition of the individual electric field vectors. So, I could add up these electric field vectors in the YZ plane, and I could just easily represent, okay, the picture like this, where I'll say here this vector represents, okay, the resultant electric field in the Y direction, whereas this vector here represents the resultant electric field in the Z direction. And you realize that this is a lot easier. We only have to draw 2 vectors, you know, as opposed to these 4 over here. But you do realize that this picture right here and this picture are equivalent. They mean the same thing. So that is unpolarized light. Okay, when we talk about light being polarized, and there are a couple synonyms that you should recognize. You will see as well, plane polarized light and linear or linearly polarized light mean the same thing. Okay, polarized light here. What do we mean by saying that light is polarized? Well, we mean that the electric field vector vibrates in the same direction at all times, okay, for a given point in space. So you'll notice in this bottom picture here, if this represents a bunch of atoms, the electric field vectors of a bunch of atoms, you'll notice that all those atoms have the electric field vector oscillating in one direction. I'm showing you here it's in the Z direction, but it could just as easily be in any direction, okay, in the YZ plane, any one dimension of the YZ plane, because that would still be perpendicular to the direction of propagation, which is the X direction. So this is what we mean, okay, for saying that light is polarized. When we talk about, here, this would represent, let's say, if this represents a bunch of atoms, and this is the net or resultant electric field of a bunch of atoms, okay, you'll notice that this net field has the electric field oscillating in one direction. When we talk about the plane of polarization, this is just by definition the plane that is formed by this electric field vector and the direction of propagation. So in this picture right here, for a polarized beam of light, which consists of a bunch of individual electromagnetic waves, if that polarized beam is propagating in the plus X direction, okay, then the plane of polarization will be the XZ direction, right? Because the direction of polarization is the Z direction, propagation X, so the XZ plane defines the plane of polarization. So let's begin by taking a look at some examples of unpolarized light as well as polarized light. Okay, what about light from the sun? Okay, polarized or unpolarized? Well, it turns out that light from the sun is unpolarized. When you get sunlight traveling to you in rays from the sun, okay, you can assume that the electric fields of those combination of electromagnetic waves will exist randomly in a plane, okay, that is perpendicular to the direction that the ray, okay, or beam is traveling. Okay, light bulbs, incandescent bulbs also produce unpolarized light. Okay, that the atoms that vibrate or oscillate do so randomly, okay, causing the electric field vectors to be in a whole bunch of different directions, okay, but perpendicular to the plane in which the beam is entering your eye. What about waves from antennas like TVs, radios, or radar? And this example kind of nicely shows, and this is something that we talk about in greater detail, the half-wave antenna in Physics 103, but the picture, the simulation nicely illustrates the fact that the electric field for these electromagnetic waves generated by this antenna are always in a single direction, a single dimension. So, okay, this is an example of polarized light. And it turns out that laser light, and we'll take a look at this in one of our demonstrations, okay, light emitted from a laser, which we know is monochromatic and coherent, it too turns out to be polarized. Now, there is another example that I didn't include in your notes because there is currently some scientific dispute as to its accuracy, but one that is rather interesting. Okay, and this is the light emanating from Godzilla's mouth. Okay, historical records suggest that it too is polarized light. All right, so what are we going to be talking about today? Okay, what are we going to be spending our time talking about? Okay, we are going to spend pretty much the rest of today talking about methods of producing polarized light from unpolarized light. In other words, methods of causing electric field vectors in a plane to be reduced to electric field vectors in a single line. It turns out that there are 4 different processes or methods that will convert unpolarized light into polarized light. The first is what we call polarization by selective absorption. Okay, a fancy name. This is polarization through Polaroid filters, as we'll see, or Polaroid material. Okay, we'll also talk about polarization by reflection, polarization by double refraction, where we look at unpolarized light which travels through birefringent media. Okay, and lastly, we'll talk about polarization by scattering. So we will now look at each of these 4 methods separately, okay, and that will basically constitute the remainder of today's lesson. So the first method of polarization that we'll talk about today is what we call polarization by selective absorption. And in this method, okay, in this process, unpolarized light is passed through a material, what we call a piece of Polaroid material, that selectively transmits waves for one particular plane of polarization. So this simulation, okay, nicely illustrates what's going on. You'll see here that unpolarized light enters this piece of Polaroid material, okay, from the left. And you'll notice that what comes out of the other side, this could be billions of atoms, but you will notice that their electric fields are all in a single direction. Okay, whereas when you look at the unpolarized light, and you're looking at a few different ways here, you'll notice that the electric fields are in many directions in that plane that is perpendicular to the direction of propagation. So how does this process happen? How does this Polaroid material work? Okay, well, this Polaroid material was developed by the Land Corporation in 1929, and I think many of you have heard of the word. You've heard of Polaroid film, okay, a Polaroid lens, Polaroid camera, and I'll tell you, it was quite amazing in the olden days when you could actually have a Polaroid camera that would take a picture and give you an instant print right on the spot without having to wait the many days to take your film to the lab to get it developed. I know, something you can't appreciate today in the digital age, where you get your you see what the picture looks like instantaneously that you just took. Okay, so the Polaroid film, what makes it work is that these are sheets of aligned, okay, all in a line, long chain hydrocarbons that are good electrical conductors. So in this picture I'm showing you here, I'm showing you for this piece of Polaroid material, the long chain hydrocarbons are in the vertical direction, okay, and what happens here is that The electrical conductivity occurs in the direction of these long chain hydrocarbons, since the electrons are free to move, okay, in that direction. So what happens is this behaves as a filter. Okay, those incoming waves of unpolarized light, any electric field components that are parallel to these long chain hydrocarbons, okay, will get absorbed. They will cause the electrons in these hydrocarbons to start moving, essentially absorbing those waves. Okay, whereas all of the components of those incoming waves whose electric fields are perpendicular to those long chain hydrocarbons, those will get transmitted right on through unabsorbed. So this is basically how the Polaroid material works. And in the next slide, we'll talk about the difference between the direction of these long chain hydrocarbons and the direction, that we call the transmission axis of the polarized light. So we said on the previous slide that when you look at an electromagnetic wave, if the component of that electric field of that wave is in the same direction as these long chain hydrocarbons, then that wave will get completely absorbed by the Polaroid filter. Now, for real unpolarized light consisting of kabillions of electromagnetic waves, we can equivalently say that the Polaroid material will absorb all components of the electric field, that are in line with the long chain hydrocarbons. Now, if we want to talk about what actually gets transmitted rather than absorbed, we can talk about a transmission axis. And the transmission axis is the axis in the plane of the Polaroid material that is perpendicular to the long chain hydrocarbons. Remember, electric fields in the direction of the hydrocarbons get absorbed, which means that electric fields or components of electric field that are perpendicular to those chains will get transmitted. So in this sample, what I'm showing you here of this pretend piece of Polaroid material, you'll notice that the long chain hydrocarbons are in the horizontal direction. If you look closely, you can see that. So we would then say that the transmission axis for this piece of Polaroid material would be in the vertical direction. So let's talk about these transmission conditions. Let's formally state them. We can say that when the electric field is parallel to the transmission axis, then it gets completely transmitted. So if we look in this simulation, and here what I'm showing you is this could represent a single electromagnetic wave, or this could represent kabillions of electromagnetic waves that are plane polarized, in which case we see here that the electric field is in the direction of the transmission axis, so it will get completely transmitted. And likewise, when the electric field is perpendicular to the transmission axis, or we can say that for unpolarized light, any component of the electric field that is perpendicular to the transmission axis will get completely absorbed. So let's take a look at this simulation here. And what you're seeing over here is unpolarized light hits a piece of Polaroid material, and notice it says vertical slits. Think of those slits as being the direction of the transmission axis. And you'll notice that the unpolarized light gets Polaroid, so what passes through, right here is polarized light, and if the second piece of Polaroid film is perpendicular to, the direction of the polarization, it will get completely absorbed. So in this simulation, this pretty much shows you the same thing. Unpolarized light strikes your first filter, polarized light comes out of the other side, and you'll notice that the second piece of Polaroid filter has its transmission axis perpendicular, to the electric field of the polarized light, in which case it gets completely absorbed. And finally, what happens when that electric field of either the polarized light, or if you want to look at the electric field of any individual wave, what happens when it's not parallel nor perpendicular, but forms some angle with respect to the transmission axis. In that case, we can say that the component of that electric field that is parallel to the transmission axis, okay, given by E cosine theta, gets transmitted. Remember, we said, when we talk about the projection of a vector onto a specified coordinate axis, that's what you get when you take the vector times the cosine of its angle with respect to that axis. So we can try to show that with this simulation here. You'll notice unpolarized light strikes your first filter, polarized light comes out of the other side, and you'll notice the second piece of Polaroid material here, the transmission axis, is at an angle, okay, with respect to the direction of polarization. And what comes out then is a component of the wave. Notice the direction of the electric field of the wave that comes out, okay, is in the direction. It's a component of the initial wave, so it's been reduced. Only that component of it in the direction of the transmission axis, that is the only component of that electric field that is going to come through. So we can kind of put this all together here with this simulation here. This happens kind of quick, but if you follow it, you see what happens when the transmission axis is rotated through 90 degrees. Look what happens to that wave that comes out. When it's in line now, okay, it all comes through. When it's perpendicular, none of it comes through, and you have all the cases in between there. All right, so in this slide, we will describe the intensity of the transmitted electromagnetic radiation in a slightly more quantitative fashion. So first of all, we need to understand, these are just some definitions when we talk about a polarizer or analyzer, and we can see that in this illustration. Both a polarizer and an analyzer is exactly the same piece of equipment. It's simply a piece of Polaroid film. But we would say the polarizer is what the unpolarized light falls upon, so that after passing through a polarizer, your unpolarized light has now become polarized. When you take a second piece of Polaroid film and let the polarized light travel through that, that's what we call an analyzer. So it's really, like I say, a polarizer and analyzer. It is virtually the same piece of equipment. It's just a question of which piece of film the unpolarized light falls on and which piece of film the polarized light falls on. And as we were saying in the previous slide, when unpolarized light travels through the polarizer, then basically only the components of the electric field in line with the transmission axis get transmitted. Okay, and then when we let that polarized light travel through a second piece of Polaroid film that is maybe at some angle with respect to the plane of polarization, then we say that only a component of that polarized light is able to be transmitted, and it is the component that is parallel to the transmission axis that gets transmitted. So, the relationship between electric field strength and light intensity. Now, this is something we talk in great detail about in Physics 103, but what we're going to do here is just use what we know about wave theory and make a logical extension here. So you know that for waves in general, we said that the intensity of the wave is directly proportional, or is a measure of the square of the wave amplitude. Now, according to Maxwell's equations for electromagnetic radiation tells us that, okay, the electric field is wave-like. That's what an electromagnetic wave is, right? It's just this oscillating pattern of both electric and magnetic field vectors. So the electric field itself changes in time in a wave-like fashion. So here's the little bit of a stretch of the imagination, but hopefully not too big of one. If we say for waves in general, the intensity of the wave goes like the square of the amplitude, we're going to say that for electromagnetic waves, the intensity of an electromagnetic wave goes like the square of the electric field vector. And when you take Physics 103, we'll talk about the relationship to the magnetic field vector as well. So the law of Malus gives us a quantitative expression for the intensity of, okay, polarized light that is traveling through either a polarizer or analyzer. So we're going to let I represent the intensity of polarized light after passing through the analyzer. Remember that the light that travels through the analyzer is by definition polarized. It's plain polarized because it has passed through a polarizer initially, perhaps to get it to be polarized. So we're going to say that I max is the intensity of the polarized light before passing through the analyzer, okay, whereas I is just the intensity of the polarized light after passing through the analyzer. Then we can say here, as we said in the previous slide, that when we look at the electric field, only the component of the electric field that is parallel to the transmission axis on the analyzer, only that component is going to be transmitted through the analyzer. So we have this relationship here, okay, and we're just going to square both sides, okay. Why? Because we said that the intensity of the electromagnetic radiation is proportional to the square of that electric field, okay, in which case we can say that I goes like, okay, E naught squared times the cosine squared theta. And here we can write our expression for intensity, okay, after passing through the analyzer as follows. Okay, I max is simply what we call E naught squared. That's the maximum intensity of our polarized light before passing through the analyzer, okay? And we've got this, we're multiplying it by the cosine squared theta factor, which may reduce the intensity, okay, of that light that passes through the analyzer. So here, we'll just say, when you talk about average light intensity, if we look at this relationship here, I equals I max cos squared theta, I max is a constant, but what is the average value of cosine squared theta? Well, cos squared theta oscillates between 0 and 1. The average value of that is simply 1/2. So we can say here that the average light intensity, okay, goes like the maximum light intensity of our polarized light before passing through the analyzer times the average value of cos squared theta, which is just 1/2. So we'll now look at polarization by selective absorption, basically letting unpolarized light pass through one or more pieces of polarizing film, which will serve as, okay, both polarizers and perhaps an analyzer. What will we actually see? So we'll break this up into a series of different demonstrations, and we'll start by asking the question, what happens when unpolarized light, and this will consist of both sunlight and light from the overhead lights, which will be unpolarized, what happens when we let that pass through, okay, a piece of Polaroid film? Does all the light pass through the filter? Let's find out. All right, folks. I want you to consider me to be a light source. And remember that in order for you to see an object like my face, then the light needs to leave my face and enter your eye. Well, in this case here, the light is entering the camera lens. So I want you to take a look at my image, okay, see the light that leaves my face, okay, when there's nothing in front of my face, okay. Then I'm going to stand behind this piece of Polaroid film, and I want you to take a look at what happens to the light intensity. Okay, here goes. So now I'm standing behind the Polaroid film, and you should still see an image of my face, but I'm betting that the intensity of that light that is leaving my face is reduced by a factor of 2. You're probably getting only about half as much light through when you look at an image of me through this piece of Polaroid film. So, does the result make sense? That light intensity is reduced to half its initial value? Considering the fact that the Polaroid filter will selectively absorb or filter out all components of electromagnetic waves in one dimension, then it should make sense that for unpolarized light, having all electric field vectors randomly arranged in a plane, that on average, the x components of all those electric field vectors should be numerically equal to the y components. Thus, filtering out either the x or y component should reduce the light intensity by a factor of 2. So what do you predict will now happen in our second demonstration when a second Polaroid filter is placed behind the first Polaroid filter with their transmission axes aligned? Should there be a change in light intensity as a result of the second filter? What do you predict? Let's find out.
All right, so what I'm going to do now is I'm going to take a second piece of Polaroid film, okay, represented here with the one that I'm holding, and I'm going to place it behind the first piece of Polaroid film such that their transmission axes are in line with each other. So let me stand behind the first piece of Polaroid film. Okay, you'll notice about how much light is able to reach the camera lens from my face. Now I'm going to stick the second piece of Polaroid film, okay, in front of it, and you should notice that because of the transmission axes, because they're in alignment, about the same amount of light is going to actually reach the camera lens.
So we see that with transmission axes aligned, hopefully you predicted that placing the second filter behind the first, okay, with the transmission axis in the same direction, would have no effect on the light intensity. So in the third demonstration here, I'll ask you, what do you predict is going to happen when this second filter is slowly rotated until its transmission axis is perpendicular to the transmission axis of the first filter? Okay, think about it and let's find out. Let's see what's going to happen here.
All right. Right now, the position of these Polaroid filters you're observing their transmission axes in line with each other. Okay, so we said that about half the light leaving my face, about half that intensity is actually reaching the camera lens. What I'm now going to do is I'm going to rotate one of these Polaroid filters so that the two transmission axes will be at 90-degree angles with respect to each other. Take a look at what happens to the light leaving my face when I do that. Okay, I'm going to slowly rotate it. Okay, slowly rotate it. Okay, and now you should see that in this position, okay, that no light should actually get through to the camera lens.
So, in line with what we've been saying, the first filter, which we call a polarizer, will convert unpolarized light into polarized light, so that all electric field vectors oscillate in one dimension, okay, in one direction. The second Polaroid filter, acting as an analyzer, should cause a decrease in light intensity passing through it as the angle theta is changed from 0 degrees to 90 degrees. And, okay, at 90 degrees, according to the law of Malus, no light should get through the analyzer, since we know that the cosine of 90 has a value of 0. So in the last demonstration here that we'll take a look at, we will verify that laser light is indeed a source of polarized light.
All right, folks, in this very last demonstration, we are going to see that laser light is actually polarized light. Now, you'll notice in the previous two examples that it took actually two pieces of Polaroid with their transmission axes perpendicular to one another in order to completely filter out unpolarized light. And that's like the light that we're seeing from the sun or from the lights in this room. But light that comes from a laser is plain polarized. So we should be able to completely filter out that light with only one piece of Polaroid filter. So let's take a look here. If you notice the beam here on the whiteboard, okay, we're now letting this laser shine through a piece of Polaroid. And okay, if we can get it a little bit darker in here, what I'm going to do is I'm going to slowly rotate this Polaroid here, and we should find out that for some angle here of rotation, some orientation of that transmission axis, we should be able to filter out that laser light. Okay, and I am getting not all of it, but we can see that's we're somewhere right around there. Okay, we were able to filter out most of it. Okay, there's a lot. Okay, and we see here that rotate it around here. We'll try. There, right about there, we can almost completely cut it out. Now, we don't have a perfect laser, so we can't get all of the light cut out. Oh, shoot. No.
We're so close.
I know.
So, as expected, we see that a single piece of Polaroid film behaving as an analyzer will eliminate polarized light when rotated so that the long chain hydrocarbons are in line with the electric field vectors of our polarized beam of light. Or said another way, when the transmission axis of the analyzer is perpendicular to the direction of the electric field of the polarized beam. So we will now take a look at a quantitative problem where we try to find the intensity of light passing through a stack of Polaroid filters using the law of malice. So in this problem here, we're told that unpolarized light with intensity I0 is incident upon a stack of 3 polarizers. All right, so the first has its polarization axis vertical. The second is at 25 degrees to the vertical, and the third is at 70 degrees to the vertical. We want to find the intensity of light emerging from the stack. So let's just show what this is going to look like pictorially, okay, before we apply the law of malice. So here we have our unpolarized beam, which we let fall incident upon our first Polaroid filter, which remember we call a polarizer, which has the effect of taking unpolarized light and converting it into polarized light such that the direction of polarization, okay, will be that of the transmission axis of the Polaroid filter. So notice here that the transmission axis is vertical. Notice that the direction of polarization of that polarized beam is vertical. So we're now going to take this polarized light and let it fall incident upon this second piece of Polaroid filter, which behaves as an analyzer here, which will selectively absorb it and reduce the light intensity according to the law of malice. So our polarized beam here with its initial intensity, okay, because the transmission axis of this analyzer is not in line with the initial direction of polarization, the light intensity is going to get reduced. Okay, and here we know that the transmission axis of this analyzer is at 25 degrees to the vertical. When we let that reduced polarized light then fall upon a second Polaroid filter whose transmission axis is also at an angle, okay, with the vertical, its light intensity, the intensity of that polarized beam, will be reduced a second time. And we will have a picture that looks like this. So I just want to point out here, so given in the problem here, this second piece of Polaroid, the second Polaroid filter, which also behaves as an analyzer, has its transmission axis at a 70-degree angle with respect to the vertical. So let's apply the law of Malus here and figure out what the intensity of this beam that emerges from the stack of 3 Polaroids will be. Okay, so what we're going to say is that I sub n represents the intensity of light after passing through the nth polarizer. So we'll start with our first piece of Polaroid film, our first Polaroid filter, which behaves as a polarizer. And we would say that I1, the intensity after passing through the first piece of Polaroid, is equal to the initial intensity, which we're told is I0, divided by 2. Now, know here that this does not involve the law of Malus. Okay, the law of Malus up here applies to polarized light. You just have to know this as a fact, that when you let unpolarized light fall upon a Polaroid filter that we call a polarizer, it will selectively absorb all of the electric field vectors in one dimension and allow the transmission of only those electric field vectors that are in a perpendicular dimension. So basically, half of your unpolarized light will be filtered out, because we're saying on average those electric field vectors are just as likely to be, have the same resultant field in one dimension, let's say the x dimension, versus the y dimension. So we are selectively filtering out, half of those electric field vectors, reducing the light intensity by a factor of 2. So I2, the intensity of the light that emerges from our second Polaroid filter, which is now behaving as an analyzer, since it's polarized light that strikes it, according to the law of Malus, I2 will be equal to I1 times the cosine squared of 25 degrees. It's very important you know what this angle is. This angle theta is the angle between the direction of polarization of the polarized light and the transmission axis. So we are told that if this electric field of the polarized light is in the vertical direction, because that's the direction of the transmission axis of this first piece of Polaroid film, we are told that the transmission axis of the second Polaroid is at a 25-degree angle to the vertical. Therefore, when we apply the law of Malus, we're going to be taking the cosine squared of 25 degrees. So I2 is equal to I1 cos squared 25. If we want to plug in our value of I1, we find that I2 is equal to I0 over 2 times the cosine squared of 25. So what happens after light passes through our third Polaroid filter, which again behaves as our second analyzer? According to the law of Malus, we say that I3 is equal to I2 times the cosine squared. Notice I put this in red here because this is where you have to be very careful. You cannot just pick any angle in the problem. Notice that we are told that the transmission axis of the second analyzer is at a 70-degree angle with respect to the vertical. But that is not the angle theta that you see here in the law of Malus. The angle theta is the angle between the transmission axis of the Polaroid filter and the direction of that incident polarized beam. So notice here that that polarized beam is not in the vertical direction. That polarized beam is now at an angle of 25 degrees with respect to the vertical. Therefore, the angle between this polarized beam and the transmission axis, which is at a 70-degree angle to the vertical, will now be the difference between the 70-degree angle and the 25 degrees which defines the polarization direction of the incident beam here. Okay, so the angle we really need to find here between the direction of the polarized light and the direction of the transmission axis is the difference between these two angles. So when we plug this in here, okay, we find out that I3 then is equal to I2, which we said is I naught over 2 times cos squared 25 times a cosine squared of 45 degrees, which when we do the number crunching has a value of about 0.2 times the initial intensity given in the problem, I naught. So the second method of producing polarized light from unpolarized light is what we call polarization by reflection. And to describe this very generally, we can say that when an unpolarized beam of light strikes a non-metallic surface, okay, the reflected light beam may be polarized to various degrees depending upon the angle of incidence. So this simulation shows you nicely what is happening. If unpolarized light is striking a surface here, a non-metallic surface, okay, as we know in the case of all waves, there's going to be a reflected beam and a transmitted beam. That reflected beam, okay, may be polarized to various degrees, okay, depending upon the angle of incidence of that incident beam. And we'll talk about, you know, what is a condition that determines the degree of polarization. So we see here that the reflected beam and the transmitted beam, okay, become partially polarized. So let's take a look at this phenomenon that we call polarization by reflection. And as you see in the diagram here, we're going to represent unpolarized light in terms of its two components. One component we'll call the parallel component. That's what I'm representing here by this dot, as if this component is going into the plane of the paper, into the plane of your computer screen. And this component here would be parallel to the reflecting surface. The other component is actually drawn in the plane of the paper itself, or the plane of the computer screen itself. And this component is obviously perpendicular to the parallel component, and it's perpendicular to the direction of propagation. So it turns out that for a non-zero angle of incidence, the reflected beam here and the refracted beam, this is the beam that is reflected and refracted from a non-metallic surface, will get partially polarized. What is interesting, however, is that it turns out that for a special angle of incidence, we call when the angle of incidence is equal to what we call the polarizing angle, or Brewster's angle, as we'll see, this reflected beam gets completely polarized. You'll notice here that only the parallel component remains. Okay, the perpendicular component is completely disappears. It's filtered out. So we want to try to explain why this happens here, okay, which we will in a future slide here. An analogy here that I kind of like, you know, all analogies are limited, but to kind of see this phenomenon here, I liken polarization by reflection to the act of skipping stones. And you know, if you've done this before, that if you just randomly throw a stone in the water, most of that stone's energy is going to get transmitted right through the surface, okay, because it's not going to skip. Similar to the case of unpolarized light, an unpolarized light beam, which shines on the surface, okay, at a random angle, most of that beam's energy, that unpolarized beam's energy, is just going to get transmitted right on through. But for the stone that is thrown at just the right angle with just the right orientation, most of that stone's energy is going to get reflected from the surface, okay, with very little of its energy transmitted through the surface. And this is what you see by this gentleman, this professional stone skipper here. This parallels the case for a beam of unpolarized light that shines at just the right angle that we call the polarizing angle or Brewster's angle. So in this slide, we will explain polarization by reflection, how this occurs, and at the same time derive Brewster's law, which tells us what that special angle of incidence is. Okay, will tell us a value for that polarizing angle. So Brewster's law is going to tell us the Brewster angle or the polarizing angle theta sub p, which, like we said in a previous slide, is that angle of incidence for which the reflected beam gets completely polarized, as this figure, okay, suggests. Okay, notice that that incoming beam has both a parallel and perpendicular component, okay, but what gets reflected is only the parallel component. So, the polarization direction, we can say that the perpendicular component of the electric field gets absorbed by the surface, only the parallel component gets reflected. Let's try to explain why this is the case, okay, why we get plane polarized light for this special angle. And we got to do a little bit of geometry here. When the incident angle here, okay, which we call the polarizing angle, plus the angle of refraction here, the refracted angle, is 90 degrees. All right, and I'll tell you here, remember, this angle of incidence here, theta sub p, is also equal to the angle of reflection, right? That's the law of rectilinear reflection. So when this angle here, theta sub p, okay, plus the angle of refraction here is equal to 90 degrees, what that tells you here is that this angle right here must be 90 degrees as well. Why is that important? Well, because when that condition is met, the reflected ray, which I'm showing you in red here, is in the same direction as the perpendicular component of the electric field in the refracted beam. So notice for this refracted beam here, the perpendicular component here I'm showing you in red is exactly in the same direction as that reflected beam. So remember, when that incident beam comes here and interacts with the molecules in the nonmetallic surface, okay, it re-radiates this reflected beam here. And since for all electromagnetic waves, the electric field must be perpendicular to the direction of propagation, okay, that is, there is no radiation in the direction of the charged particle acceleration, okay, there cannot be a reflected ray with any component of E perpendicular. So once again, let me say this, let me repeat what I just said. All electromagnetic waves, the electric field must be perpendicular to the direction in which the wave travels here. Okay, there can be no component of that electric field in the direction of propagation. So what that means here is that this component of the electric field here, this perpendicular component, cannot exist in the reflected beam, since it would be exactly in the direction of propagation. In which case, the only possibility is that the parallel component, that can exist, because the parallel component here is perpendicular to the direction of propagation, okay, in line with, allowed by what we know about electromagnetic waves. So the relationship between the reflected and refracted rays, as I showed you, theta p, the polarizing angle, Brewster's angle, occurs when the angle between the reflected and refracted rays is 90 degrees, right here. And we can then figure out, okay, using a little bit of geometry or trigonometry, what that angle is. So Brewster's law is really nothing more than Snell's law applied to this special situation. So if we say that the unpolarized beam is in an incident medium with refractive index N1, and the transmitted medium has index of refraction N2, we see here Snell's law. We will make the substitution for the angle of incidence, we'll call theta sub p. That's the symbol we use for the special polarizing angle, or Brewster's angle, as it's sometimes called, is equal to n2 times the sine of theta 2. And you'll notice here that theta 2 from this diagram, if I look at these three angles here, okay, in this line here, we've got theta sub p plus this angle right here, which is 90 degrees, plus theta 2, which is theta refraction. So here, notice that the angle of refraction, theta 2, is equal to 180 degrees, okay, minus our angle of reflection, minus this 90-degree angle. So, okay, Snell's law reduces to this here. N1 times the sine of that polarizing angle is equal to N2 times the sine of theta 2, which we said is 90 minus theta sub p. And when we look at these trig identities here, sine of 90 minus theta sub p is none other than cosine of theta sub p. And when we take this ratio of sine theta sub p to cosine theta sub p, that is simply tangent of theta sub p. So here we have Brewster's law. Tangent of theta sub p is simply this ratio of, okay, the index of refraction in our transmitted medium to that of our incident medium. So this relationship here, very simple as it is, tells us what that angle of incidence is that leads to this condition where the reflected beam will be completely polarized. In the next slide, we will try to demonstrate this phenomenon called polarization by reflection by looking at unpolarized light that is reflected off of a smooth surface, and with the help of a Polaroid filter, okay, being able to determine the degree of polarization of the reflected light. So what you're looking at here is light from a focusable flashlight that is reflected off of a glass surface. And you see the Polaroid filter which is put in front of it, which is being rotated. Of course, we do not have the exact polarizing angles, so we cannot filter out all of the light, but you will see that the light that is reflected from the smooth glass surface is partially polarized, as you see the reduction in light intensity through the Polaroid filter. And lastly, we'll take a look at a couple of applications of this phenomenon we call polarization by reflection. So first application here has to do with Polaroid sunglasses, and we're asked to find what is the orientation of the transmission axis in Polaroid sunglasses. This may be something that you've noticed if you've got polarized sunglasses. So if what we're saying is that it is that parallel component of the light that gets polarized by reflection. Okay, so when we look at the reflected beam off of that smooth surface, okay, whether it's water or snow, a non-metallic surface, if it's the parallel component that is strongly reflected, then it would make sense that to eliminate that parallel component, we would want our polarization axis, the transmission axis, to be in the vertical direction to eliminate that parallel component. If you say, why would you want to eliminate that? It's because the reflected component of the unpolarized light is what we refer to as glare. So if you want to reduce the glare off of a non-metallic surface, okay, then you need to get rid of the strongly reflected parallel component, and that can be done by setting the transmission axis of your polarized sunglasses in the vertical direction. And the second question is really kind of a follow-up question. Why do fishermen use polarized sunglasses to see better underwater? Well, think about it. If you can reduce the glare coming off of the surface, that reflected light, then you're going to be able to actually see down into the water. Okay, so by getting rid of that strongly reflected parallel component, okay, which serves as the glare, you will be able to see much better underwater. So see those little fishies swimming around that you're trying to catch. So we've talked about polarization by selective absorption, where unpolarized light can be polarized by passing through Polaroid filters. We've also talked about polarization by reflection, where unpolarized can become at least partially polarized when reflected off a non-metallic surface. Now we're going to talk about a third method of polarization called polarization by double refraction. So, what's going on in this method? Upon entering what we call a doubly refracting, or as a synonym, a birefringent medium, unpolarized light gets plane polarized. So let's talk briefly about birefringent materials. A birefringent material, a birefringent medium, is a crystalline material containing more than one index of refraction. It turns out that the index of refraction varies with the direction that the light travels in the material. The important consequences of this, and it's the same when we talked about refraction of light in general, is that if the index of refraction is not constant, okay, then the speed of light is not the same in all directions. Okay, just as different wavelengths of light traveling at different speeds causes them to get refracted by different amounts, remember, this is the phenomenon we call dispersion. When different components of the electric field traveling at different speeds, okay, this causes them to get refracted by different amounts as well. So looking at some examples here of birefringent materials, calcite, okay, calcium carbonate, you see here on the right, okay, that we have really two indices of refraction, N sub O and N sub E, and we'll talk about this. O stands for ordinary, E for extraordinary. We'll get to that next slide. And you'll notice that while the indices of refraction are, not that different, okay, they are different. Quartz, silicon dioxide, again, notice two indices of refraction, sodium nitrate, sodium sulfide, zinc chloride, and zinc sulfide are also examples of doubly refracting or birefringent materials. So I think this diagram should help us understand how unpolarized light becomes polarized with this method that we call polarization by double refraction. So we start with a birefringent material, in this case a birefringent crystal, and I'm going to show you, we're going to let unpolarized light be incident upon this crystal. All right, so here is our unpolarized light, and we will represent it this way. Okay, there's two mutually perpendicular directions of that electric field vector, which really shows us that the electric field is somewhere in that plane. Okay, and when we let this unpolarized light reach our crystal here, it turns out that our unpolarized light is going to split into two different rays. One of these rays, what we call the ordinary ray, obeys Snell's law. Now, I just happened to show you this unpolarized light, okay, entering our medium at a zero angle of incidence. In other words, it is entering right along the normal line. So according to Snell's law, the angle of refraction should be zero. So it turns out that one of these components of the unpolarized light, okay, what I'm showing you here, this parallel component, is the one that will obey Snell's law, and that component will travel straight on through, obeying Snell's law, and you can see then that this ray here that we call the ordinary ray is now plane polarized, right? Because the electric field is in one direction. The other ray, what we call the extraordinary ray, does not obey Snell's law. Now, obviously here, if the incoming unpolarized light has no angle of incidence, then we would say that, okay, a ray that gets refracted by a certain amount is clearly not obeying Snell's law. This is what we call the extraordinary ray, and it turns out that the angle of refraction will depend, okay, upon the angle at which that unpolarized light enters the birefringent medium. So the end result is that unpolarized light gets polarized into two mutually perpendicular directions. In a sense, you know, we have this unpolarized beam which really creates two mutually polarized beams. Okay, so notice that one beam is polarized in one direction. The other beam, which also represents polarized light, is polarized in a direction that is perpendicular to the first beam. In other words, the extraordinary ray has a polarization direction which is perpendicular to that of the ordinary ray. So a little more about ordinary and extraordinary rays. Okay, it turns out that the ordinary ray has an index of refraction that is the same in all directions. So regardless of the angle of incidence of that unpolarized light, the index of refraction will be the same for all angles of incidence, which then implies that the speed of, okay, that ordinary ray, okay, will be the same in all directions, which will mean that it's going to obey Snell's law, okay, of refraction. The extraordinary ray, however, the index of refraction is not constant and does vary with the direction of propagation. So we can see here that given that, if the index of refraction varies with the direction of propagation, so will the speed of the ray, which means that for different directions of propagation, different angles of refraction will result. So you can see here that, you know, given the fact that you get many angles of refraction for this extraordinary ray, clearly it does not obey Snell's law. So an interesting demonstration of this, to see this, and I'll ask the question here, we'll do this as a simulation here. What would happen if you placed a birefringent material on top of these words below? So let's think about this. We've got these words written on a piece of paper. I'm going to place a birefringent crystal on top of that, and you will basically see this pattern on the screen. Hopefully that makes sense to you, because the light that leaves those words coming from, you know, sunlight and other sources of light in the room will be unpolarized light. When that unpolarized light passes through that birefringent material, it will now get polarized into two mutually perpendicular directions. So one of those, the words double visions, one of those images represents the ordinary ray, the other image represents the extraordinary ray. And remember, the ordinary ray will be formed by the image that actually obeys Snell's law in this case. So in the next slide, we will try to demonstrate this for you in real time so that you actually, okay, believe that this actually occurs. All right, so I'm going to be coming at you from the middle of the screen in the slide when we talk about this last method of polarization that we call polarization by scattering. So what's going on in this method of polarization? When viewing sunlight scattered from gaseous molecules in the atmosphere at right angles to the initial direction of propagation, okay, that sunlight, when viewed at right angles, becomes plane polarized. So let's take a look at what this means in the form of a diagram here. So this is just one example of an oxygen or nitrogen molecule in the atmosphere. And if we have unpolarized sunlight, and we will arbitrarily choose this as our initial propagation direction, here is our unpolarized beam of light. Notice we'll use this representation where we have a, let's say, a horizontal and a vertical component. Okay, and it turns out that when that unpolarized light gets absorbed by that molecule or those molecules in the atmosphere, it gets absorbed, causing the electrons in the molecule to start oscillating, which creates a new electromagnetic wave or waves. So the end result is that upon being absorbed, a new electromagnetic wave or waves is created and re-radiated. And it turns out that the re-radiated or new electromagnetic wave becomes plane polarized. You'll notice that, okay, the vertical component, okay, of the unpolarized light has been filtered out here. And if you look at this, and we'll state this formally in a second, but this should remind you a little bit of what we saw with polarization by reflection. That when unpolarized light got absorbed by the surface and then re-radiated, okay, that there was a certain angle for which that reflected beam became completely polarized. And it turns out it became completely polarized for the same reason that we have here. That this vertical component here cannot exist in the direction of propagation. So when viewed at this angle, at this 90-degree angle to the incident direction of the unpolarized light, there can be no component of electric field in the direction of propagation. That is a property of all electromagnetic waves, which we'll formally state right now. So what's going on here? Sunlight gets absorbed by the oxygen and nitrogen molecules and then re-radiated as new waves. Once absorbed, the electric field of the incident electromagnetic wave sets the charges in the molecule oscillating. The horizontal component of the electric field sets the charges oscillating horizontally, while the vertical component of the electric field sets the charges oscillating vertical. So what we're saying is that each of these directions of the electric field sets the charges oscillating in that direction. The oscillating electric charges create a new electromagnetic wave. Remember, that is the source of all electromagnetic radiation, is accelerating charged particles. So when these charged particles in these gaseous molecules in the atmosphere start vibrating back and forth, start oscillating back and forth, okay, they create new electromagnetic waves. When we consider what we know about electromagnetic radiation, okay, when an electromagnetic wave propagates in a direction, there can be no component of the electric field that exists in the direction of propagation. Since for all electromagnetic waves, there is this basic property, the electric field must be perpendicular to both the magnetic field and to the direction of propagation. So when you look at the picture here, we see that this vertical component of the electric field cannot exist in the direction of propagation, in which case, okay, we can say when viewed at this angle, only this horizontal component here, which is perpendicular to the direction of propagation, can exist. So in this sense, our beam of unpolarized light becomes polarized when viewed at this angle. So when viewed at right angles, this sunlight that gets scattered by these molecules in the atmosphere becomes plane polarized. So in this slide, I'm just including a simulation that gives you another illustration of polarization by scattering. Sometimes this is called Thomson scattering. So you see here that the unpolarized light coming from the sun sets the electric fields oscillating, and okay, it causes only one component, electric fields with components in one direction, to be transferred into the eye when we are viewing this at right angles to the initial direction of propagation. So in this next slide, we will use a very outdated piece of technology that may not be familiar to you. It's something called an overhead projector. And we'll use some water with a little bit of coffee creamer to try to recreate this polarization by scattering effect. And with the help of a Polaroid material, we will be able to determine whether scattered light, okay, is plane polarized or not. All right, so you can see the light projected through the bottom of this glass container filled with water and coffee creamer. When we look at this light at right angles, we should find that the scattered light is polarized, or at least partially so. This mimics what you would observe when you look at light scattered from the sky at right angles to the sun's rays. Notice in this demonstration that a single piece of Polaroid, when rotated to the correct angle, is able to filter out the great majority of the scattered light, suggesting that it is plane polarized. Right, and we'll finish up our discussion today by taking a look at some rather interesting and important effects of scattered sunlight. Okay, like why does the sky appear blue at certain times and certain viewing angles? Why will it appear red at others? So I'm going to state this relationship between scattering intensity, the intensity of scattered sunlight, I'll call eye scattering, and the wavelength of light. And I'm going to state this as a fact here without giving any proof. But it turns out when the wavelength of the light is much, much greater than the dimensions of the atmospheric molecules that are causing the scattering, it turns out that the intensity of the scattered light is inversely proportional to the wavelength to the fourth power. So, when you're looking at the sky in a direction that is not towards the sun, okay, like if the sun is overhead during the day, okay, not when it's on the horizon, the sky will appear blue since the short wavelength blue light gets scattered more than the long wavelength red light. Okay, and you can see here that there's the inverse relationship between scattering and wavelength. So the smaller the wavelength, okay, the greater the scattering intensity of the light. So blue light is going to get scattered more than red light, in which case a lot more blue light is going to be entering your eye, making the sky appear blue. You could explain red sunsets. Well, here, when you're looking towards the sun now at a sunrise or sunset, the light has to travel through lots of atmosphere. So most of the blue light has been scattered by the time the remainder of the light reaches you, leaving mostly red light left. Okay, so, and if you've ever lived somewhere where you have a lot of particulate pollution in the atmosphere, you'll know this effect is intensified. You'll get some really brilliant sunsets. This is one of the things I miss terribly about living in Africa, where, you know, the burning of wood and so forth causes enough air pollution that you do get some really, really brilliant sunsets. We'll try to demonstrate this for you with none other than some glue sticks. Why then do clouds appear white? Well, it turns out that since clouds involve large water droplets as opposed to small oxygen and nitrogen molecules, the above scattering relationship, okay, that we said involving the scattering intensity and wavelength does not hold. Okay, in which case the clouds will scatter nearly all the wavelengths of light equally, okay, uniformly. And if all of the wavelengths of light are getting scattered, when you add up all those wavelengths, when you superimpose them, then you end up getting white light and the clouds are going to appear white. We're going to try to demonstrate the scattering of sunlight, that is white light, okay, using a glue stick here to represent the atmosphere and a pen light, a source of white light down at the bottom. So let's turn off the lights, and what you should notice is that down here on the bottom of the glue stick, the part that is closer to the light source,
the light that is actually entering the camera lens at right angles to it is going to appear more bluish in color. Why? Because down at the bottom, a lot of that blue light is being scattered, okay, when the light does not travel through much material. Okay, but you'll notice that up here at the top of the glue stick, far from the light source, okay, where that light has traveled through a lot of material, a lot of that blue light has been scattered away, leaving only the red light left. Okay, and that is why the top of the glue stick appears much more reddish in color, which is what happens when you're observing a sunrise or sunset. When the sun is low in the horizon and travels through a lot of atmosphere, okay, most of the blue light has been scattered away by the time that light reaches your eye. So it's really only the red light that is left.